Hello students, this is Mr. Ezra. Today we're going to talk about complex numbers. Complex numbers are composed of real numbers and imaginary numbers. So let's first begin by talking about what an imaginary number is. You may have seen this before, there's a good chance you have. Imaginary numbers are really the imaginary number is called I, and I represents the square root of -1. So it is not possible using normal calculations for us to take the square root of a negative number like -1. So mathematicians kind of got around this by saying, well, let's pretend that this square root of -1 is something, and we're going to call it an imaginary number. We're going to use I to represent it, and it opened up a whole new type of mathematics that we could do using these imaginary numbers. You'll find that we can do things like square I, and I squared is the square root of -1 squared. That's what I squared is. Well, when you square a square root, they cancel each other out, so it's just -1, right? In fact, what happens with this is kind of cool. We start with I. I to the first power is I. I to the second power, we just said, is -1. Okay. We can think of I to the third by breaking it apart as I squared times I. These rules for exponents work for imaginary numbers just like they do with variables. So 2 plus 1 is 3 is how we can break that apart. Well, I squared we said is -1 and I is I, so I to the third is -1I or -I. We can think of I to the fourth as I squared times I squared. We can break it up as I squared times I squared. Well, I squared we already defined as -1. So it'd be -1 times -1. Negative times a negative is positive. So we get +1. So far we've got I, -1, I, 1. And with I to the fifth, we can think of this as I to the fourth times I, because I to the fourth times I is I to the fifth. And I to the fourth we just defined to be 1. 1 times I is I. So what's going to happen if we continued this is the pattern would repeat. We're back at I now. So I to the sixth would be -1. I to the seventh would be -I. I to the eighth would be 1. And if we kept going, it would start all over again. This is called a modular pattern. We're not going to talk too much about what modular patterns are, but that's what this is. And you can remember this modular pattern with the mnemonic device, I won, and it was a negative sandwich, right? I won, and sandwiched in between those two in the middle are negatives. And that's this pattern, I, -1, I, 1. So let's talk about how to use I, this imaginary number that we now have defined. And we can use I to handle quantities that sometimes show up in mathematical solutions. Sometimes when you're taking a square root, for example, with a quadratic formula, you end up with a negative under the square root sign. So what we can do is we can snap apart that -1, the square root of -a, we can think of as the square root of -1 times the square root of a. The square root of -1 is I, so that's the same thing as I times the square root of a. So let's try a few of these. I can think of the square root of -49 as the square root of -1 times the square root of 49. This is a property of radicals that if you multiply a radical times a radical, the inside parts multiply together. So -1 times 49 is -49. We're just breaking it apart that way. What is the square root of -1? It's called I. And the square root of 49 is called 7. And you know in algebra, the more appropriate way for us to write a letter times a number is to put the number first. So that would be 7I would be that guy there. We have the square root of -18. We can think of the negative as being the square root of -1. 18 is not a perfect square, but there is a perfect square that divides into it, and that perfect square is 9. In fact, it's 9 times 2. So we can think of this as the square root of -1 times 9 times 2, because 9 times 2 is 18. And negative times 18 is -18. So it all works out, right? We're just kind of breaking it apart. And when we break it apart, our goal is to have the imaginary number, something that divides evenly that is a perfect square, and then whatever is left over. Doesn't have to be perfect square. It's just something that's left over, right? So, square root of negative 1 is an I. Square root of 9 is a 3. But this doesn't have a square root. It doesn't come out. It's going to stay underneath the square root. So the best way to write this, in my opinion, is to put the 3 first, the I after the 3, and then attach the square root on at the end. And we do this for a few reasons. One is if you put the I at the end, it might look like it's underneath the radical sign. By putting the radical at the end, there's no ambiguity there. You know exactly what the parts are. It's 3i and root 2. Right, so that's kind of how we would handle these imaginary numbers in a square root. Now we're going to kind of progress and talk about what is called a complex number. That's kind of our goal today. What is a complex number? Well, a complex number combines real numbers with imaginary numbers. So there's going to be a real part, could be any real number, and there's going to be a plus or a minus sign, which is like a plus sign, and an imaginary part. It can have a coefficient in front, but there's going to be the letter I. Okay, so some examples. 3 plus 4i. 3 is the real part. 4i is the imaginary part. So we've got real plus imaginary. In our second example, negative 6 plus 3 halves I. Negative 6 is the real part. Okay. And then 3 halves I is the imaginary part. You can, real numbers include decimals and fractions as well. So 4.5 is our real part, and negative I times 2 square root of 6 is our imaginary part. So that's all the imaginary part. And if it helps you to think about it this way, you could think of this minus sign here as plus a negative, so that you've got the plus there, right? Plus a negative gives it the negative imaginary part. Now, something to think about, add this over here, box. Something to think about is the number 5 complex. In the same kind of thinking is the number 7i complex. Well, to be complex, a number has to have two parts, right? A real and an imaginary part. Does the number 5 have a real part? Well, yes. 5 is the real part, right? Does it have an imaginary part? Well, it does have an imaginary part. It's just, you don't see it there, right? It would be 0i. So in this case, 5 is complex. The imaginary part just has a value of 0. So I guess you can see where I'm going with the same type of question. Is 7i complex? Well, yes, 7i is complex. 7i is the imaginary part, right? What's the real part? Well, the real part is 0. So you can have a real part that is 0 or an imaginary part that's 0 and still have a complex number. This means that almost any number we deal with is going to be a complex number. So let's write these complex numbers in standard form, right? What does that mean? It means that we've got to change this square root part to have the letter I. Okay, so we want the form a plus bi. Well, in our first example here, we've got 9 minus the square root of negative 75. Well, we're going to treat this minus sign as plus a negative, but we're just going to put minus, right? But we have to deal with the square root of negative 75. So remember, we want the square root of negative 1 to take care of the negative. We want a perfect square. In this case, it's going to be 25 goes into 75 3 times. And the leftover part is 3. 25 times 3 is 75. This has to be a perfect square. All right, so that gives us 9 minus. Remember, we put the square root of 25 first as 5, then the imaginary part, and then the leftover part. So this would be our standard form right here. 9 minus 5i times the root of 3. All of this together helped us deal with the square root of negative 75. We'll do the same thing with the next question. Negative under the radical, square root of negative 1. Now, is 144 a perfect square? It is, right? So I don't need a perfect square that goes into it. Itself is a perfect square. When I write it, I put not the I goes second, and the square root of 144, which is 12, goes first. So 5 minus 12i. The square root of 16 plus 7, you might begin to see that you could think of this as a shortcut. You know, a lot of times what I see students do is they'll say, oh, well, this negative here is going to come out as an I. Get rid of it. And they'll say the square root of 16 is 4. So they just go ahead and go up here and say I times 4 rather than coming off to the side. So that's 4i plus 7. Now that is not standard form, right? For standard form, the real part has to go first. So we use the commutative property to say 7 plus 4i instead of 4i plus 7. And our last question on this slide is negative square root of negative 100. Again, the negative is going to come over, right? That's set in stone. This negative outside is over. But what's inside, we can go ahead and just kind of simplify right here. The square root of a negative is going to have an imaginary part. And the square root of 100 is 10. So instead of I times 10, we'll write 10i. Circle up all of our answers. Now, negative 10i is in standard form. We just realized that the real part is 0. We don't ever have to write a 0 by itself. It's unnecessary to do that. Next up, we need to add some complex numbers together. You add these just like regular binomials or polynomials where you have variables and real parts. So you add the real parts together. So essentially what's going to happen here, since there's nothing in the parentheses that we can do, we're going to drop those parentheses. And then we're going to add together the like terms, okay? So essentially what's going to happen is the 2 plus 4 are going to be added together, and the negative 4i plus 3i are going to be added together. A lot of students will just go ahead and do that here. I'm just showing you that the 2 and the 4 go together, and the negative 4i and the 3i go together. They're like terms. We're going to add them together. 2 plus 4 is 6. Negative 4i plus 3i is negative 1i, and we don't write a 1 in front of a variable. It's understood to be there. We just write negative I. And we can make this look even a little bit better by saying 6 minus I. And we've added those two complex numbers together. Subtracting complex numbers is similar, except we have to deal with this negative in the middle, right? Because let's go back for just a second. You know, when I have a plus, if I think of this as a positive 1, 1 times 4 is still 4, and 1 times 3i is still 3i. But when I have a negative in the middle, if I think of that as a negative 1 and I distribute that negative 1 into the parentheses that follows it, it's going to change the signs of what follows. So we do need to think about that as we're working the problem. So the negative 3 plus I is fine. No worries. But we have to distribute this negative here, and we get a negative times a negative is a positive 8. Negative times positive is a negative, and 1 times 2i is 2. Again, like terms, we've got negative 3 goes with positive 8. And we've got I that goes with negative 2i. The i's go together, the imaginary parts go together, and the real parts go together. Well, negative 3 plus 8 is 5, and I minus 2i is negative I. And that would simplify to 5 minus I. So now we've added and subtracted, and really those are similar things. You just have to distribute the negative 1 when you're subtracting. We can multiply complex numbers. Now, when you multiply complex numbers together, you might remember from previous classes a procedure for multiplying binomials called FOIL. FOIL stands for first, outside, inside, last. And we can use that process here. We can multiply the first times the first, the outside times the outside, the inside times the inside, and the last times the last. Essentially everything in the first parentheses times everything in the second parentheses. So what is 9 times 7? 63. 9 times 15i is 135i. Negative 12i times 7 is negative, let's see, 70 plus 14, 84i. A negative times a positive is a negative, and 12 times 15 is negative 180i squared. All right, so 12 times 15, 180, negative times positive, negative, of course, and then I times I is I squared. Right. Now, go back to the very beginning of our lesson today. What did we say about I squared? I squared is the same thing as negative 1, right? So we're essentially going to change this to be a negative 1. And what is a negative times a negative? Positive. So that I squared at the end is going to change this negative 180 to become a positive 180. So bring everything else down. Now we have some like terms here. The real parts go together. 63 plus 180, and instead of rewriting it, I'm just going to add them together here. 63 plus 180 is 243. 135i minus 84i, those are like terms, they go together. That is positive 51i. Oops, 51i. So we have multiplied using FOIL, first, outer, inner, last. Another operation that we do is we can square the imaginary number. So squaring is a lot like multiplying, right? So I'm going to come over here. We can think of this as 2 plus 3i times 2 plus 3i. And that's great. You can FOIL that just like you did a minute ago. But anytime you square a binomial, there's a shortcut that you can use that maybe you've picked up in the past. And this is what it looks like. It's a fast way to do it if you want to learn how to do it, rather than actually multiplying it out. Multiplying it out is fine. Nothing wrong with that. This is just faster. So we're first going to square 2. 2 squared is 4. We're then going to multiply 2, the number 2, times the first times the second. Okay, so that number 2 is like always there. It's a 2 no matter what. So 2 times the first, which is, in this case, also a 2, times the last, which is 3i. And then we're going to add the last part squared. So 3 squared is 9, and I squared is I squared. That's a way to do it fast. It's square the first part plus 2 times the first times the second plus the second squared. Okay. And you get really fast at it as you practice it. It gets a little bit more quick. Okay, so that's 4 plus 2 times 2 is 4 times 3 is 12. Well, what do we say about I squared? I squared is the same thing as negative 1, and positive 9 times a negative 1 is a negative 9. The only like terms we have here are the 4 minus the 9, which is negative 5, and that's going to go first because it's the real part. 12i will go second because it is the imaginary part. So you can square by multiplying the binomial times the complex number times the complex number using the FOIL process. First, outside, inside, last. Or you can apply this property of squaring a binomial. And finally, we have a process called division. Now, division is a little different. We're not actually going to divide these complex numbers. Instead, we're going to multiply the top and the bottom by something that's called the complex conjugate. Okay, so we're going to take the top, 3i. And we're going to take the bottom, 5 minus 2i. And we're going to multiply by the complex conjugate, which is the bottom. Okay, complex conjugate of the bottom, which is the bottom, with the sign changed. You have to remember to do this. Okay, so 5 plus 2i would be the complex conjugate of 5 minus 2i. Okay. Now the top, we use the complex conjugate of the bottom again. So multiply top and bottom by the complex conjugate of the bottom. Now you'll see why we do this in just a second. Okay. Let's start by multiplying the top. in the top, this multiplication looks a lot like distribution. We've got 3i times 5 and 3i times 2i. So 3i times 5 is 15i. And 3i times 2i, well, 3 times 2 is 6. So plus 6i times I is I squared. And we'll deal with that I squared. We'll simplify that in just a second. Right? For the bottom part, when we multiply by the complex conjugate, we get 5 times 5, which is 25. This is the FOIL process. That's the first times the first. Outside, 5 times 2i is 10i. Inside, negative 2i times 5 is negative 10i. And last times last, negative times a positive is a negative. 2 times 2 is 4. I times I is I squared. What's going to happen here is kind of magical. It's kind of awesome. These two middle parts, when you multiply a number by its complex conjugate, like we did here, well, the middle parts are going to cancel out. Always. In fact, when you get good at this, you don't even write this anymore because you realize it's not going to be there. And all that we have left is 25 minus 4i squared. At the top, we have 15i plus 6i squared. Now, we got to fix these I squareds. Whenever you end up with an answer with an I squared, it's always going to change to a negative 1, which means any number in front of it is going to change that sign. So 6 times negative 1 is negative 6. So we have 15i minus 6. And on the bottom, 25, negative 4 times negative 1 is a positive 4. So 25 plus 4. All right. Well, so 15i minus 6, that's not in the right order, is it? It should be negative 6 plus 15i. Remember to keep your signs when you use the commutative property. So the negative is going to stay with the 6 when it goes to the front. In the bottom, we no longer have an imaginary part. It's all real. 25 plus 4 is 29. Now, technically speaking, this is a good answer. We've divided, but we like our answer to be in a complex number form. And there is a real and imaginary part on the top, but the bottom is kind of messing that up. So all we're going to do is we're going to split this into two fractions, right? It'll be negative 6 over 29 plus 15i over 29, or 15 over 29i. So now we have a real part, negative 6 over 29, and we have an imaginary part, 15 over 29i, and that is a great answer to this division problem. So dividing, there you can see there's no division here. We're actually multiplying by something called the complex conjugate of the denominator, and we multiply it on the top and the bottom. And what happens when we do this is we end up eliminating the i's in the bottom because the i's cancel out and the I squared fixes, gets rid of that I there, and now we magically have a whole number in the bottom, so we can use these fractions to represent our complex number. Well, that is it for today. Whirlwind of complex numbers. Hopefully it wasn't too bad, and I'll see you in class.